Let's continue the phonons in 3 dimensions. As we mentioned last time, in 3 dimensions, we need to diagonalize the Hamiltonian twice. The first was the the side diagonalization, and another is the performing the axis rotation, and like a rigid body rotation, and to actually diagonalize the direction of these vibrations. Okay, so in general, we have 3 phonon modes for a fixed q vector, a momentum of the phonon, and the dispersions show in general, 3 different branches of this absolute value of a psi. Remember, this is absolute value of a psi, qa/2. And we also defined the 3 polarization directions, which are the directions of the lattice vibration. And q is actually the direction of the wave propagation. Okay, so it is kind of a phonon vibration, is some kind of sound propagation or kind of electromagnetic wave propagation, where this energy or momentum of that lattice vibration is pointing to a particular direction, q, but the lattice vibration can actually follow a different direction. Okay, it can be the same directions or it can be different directions. Okay, so if the direction of the lattice vibration is the same direction of this momentum or the wave propagation direction, then we call this longitudinal phonon mode. On the other hand, if the s direction is actually perpendicular to the momentum or the wave propagation direction, then we call this as transverse phonon. Okay, so we will give you some concrete example of both longitudinal and transverse phonon mode, but to illustrate this in the cartoon picture, in terms of this kind of wave propagation as a phonon mode, we could have the longitudinal mode where the atoms are moving along this kind of a sine wave direction, where the s vector, which describes the direction of the lattice vibration, is actually along the x-axis, which is the same direction of the wave propagation, where this kind of a phonon wave, kind of a momentum direction, or this wave propagation direction. Okay, so this is kind of example of longitudinal phonon mode, and we will come back to this later. Okay, but there is another example of a transverse phonon mode where the atoms can actually vibrate along the y-axis or the perpendicular to the x-axis, where the x-axis horizontal line represents the propagation direction, which is the direction of the wave propagation. Okay, so you can see that the propagation of the wave or the phonon mode is actually along the horizontal line, whereas the atoms actually move up and down along the transverse direction or the perpendicular direction to the wave propagation direction. Okay, so this is called the transverse phonon. Again, so these kind of phonon branch most likely is longitudinal, and we will give you some example of a transverse phonon mode later. And the reason is that the low energy excitation is actually linearly proportional to q, so omega is actually linearly proportional to q, and this is called acoustic phonon mode. Okay, so we will come back to this later. To see this kind of a different longitudinal and transverse phonon mode, a good example is a little bit complicated non-simple Bravais lattice case where the phonon can actually exist in such a interlocked 2 lattices. In this non-simple Bravais lattice, we have 2 interlocked Bravais lattice, the yellow open circle lattice points, and the solid circle and solid line lattice. Okay, so you could consider that I can simply just overlap these two lattices and then shift it one lattice from another by a vector. And we can define the central mass of these two lattices and mark by red, and this lattice spacing or lattice vector of this combined lattice structure is given by this L vector. But along the central mass direction, we can actually define each individual different sublattices, open circle and solid circle, by two small lattice shifts, B1 vector and B2 vector, like this. All right, so we can equivalently consider this kind of interlocked Browser lattice as a linear combination of two simple Browser lattices, as I mentioned. You simply just put one lattice on top of the another, and then shift it by a vector. So that's the simplest version of the non-simple Browser lattice. All right, so you can consider the lattice vibration of the open circle atoms and also the solid circle atoms, and they have this displacement vector, say YB1 and YB2 respectively, and we simply have to sum over all lattice vibration of all atoms for this open circle sublattice and the solid circle atoms. And we could follow the same approach that we did before by performing this kind of Fourier transformation of this displacement vector. But now, in this kind of a non-simple Browser lattice, we have two sublattices, and therefore this displacement vector y carry the index I, where I runs from 1 to 2, representing these two different sublattices. And we have the subscript bi or b1 and b2 attached to that y of q. Okay, so if we have just a simple Browser lattice, then there's no such a bi index here. But since we have two different sublattices, we need to distinguish these two displacement vectors. And also the potential term, if we Fourier transform this, shows this kind of non-trivial matrix element. It depends not only on this L and L prime, but also B and B prime, where B could be either, say, B1 or B2, so is B prime. So both normal mode variables and the potential term, the matrix element of the potential term, become more complicated because we need to diagonalize the sublattice structures, say VBB prime, in such a way that we can have a diagonal eigenvalues, but this can be done straightforwardly, so we assume that we can do it, and so we simply just diagonalize this. We pretend that we diagonalize this whole thing, and then we could actually write down this Hamiltonian, but this is the term, the Hamiltonian, before we diagonalize it, but imagine that we can diagonalize it. And so the total number of degrees of freedom is actually 3 times MB, where MB is the number of atoms within each basis, such as the, say, the unit cell. So in this case, the unit cell contains 2 atoms, the open circle and the solid circle one. So therefore, MB is actually 2. So in addition to the 3 normal mode or Phonon mode that we discussed earlier for a simple Browser lattice, for this 2 sublattice non-simple Browser lattice case, we have for a fixed momentum q, we have 6 modes because we have 2 sublattices, and each sublattice we have 3 Phonon modes, and therefore altogether we get 6 Phonon modes for a fixed momentum q. So the total number of normal modes is actually 6n, where n is the number of sites. So then we could actually calculate this, say, the dispersions of this more complicated non-simple Bravais lattice, but to save time, we don't carry out all this detailed calculation, but I only summarize the qualitative features of this 6 phonon modes. And we'll see that 3 of them correspond to such low energy excitations, and we call them acoustic phonon mode. Another 3 appear at the high energy or high frequencies, and which we call them optical phonon modes. Okay, and acoustic phonon modes are actually the longitudinal phonon, and while the optical phonons are precisely the transverse version of the phonon mode. And let's take a short break. When we come back, we will sketch these 6 phonon modes. Okay, so let's just sketch the 6 phonon modes, and in terms of the dispersion. And as I mentioned, there are 3 low energy excitations, and we call them acoustic phonon modes. And there are 3 higher energy excitations, we call the optical phonon modes. For this acoustic phonon modes, it has the property that the phonon energy, omega, or frequency, is linearly proportional to the momentum q in the low momentum limit or low energy limit. And this becomes very useful for later calculations for the thermodynamic properties. And we will see why we call these low energy 3 modes as acoustic phonon modes, and why do we call this high energy modes as optical phonon modes. So let me just describe how they vibrate for these 2 different modes. For the low energy acoustic phonon modes, for example, if we simply just write down this basic unit cell of this non-simple Bravais lattice, 2 sublattice structures, the open circle and solid circle as a unit. And for acoustic phonon modes, so the central mass of this unit cell actually move together. So it's actually something like this. The open and solid circles actually move horizontally back and forth together. Okay. So central mass move together, and therefore their relative phase is actually 0. So it's an in-phase vibration. So this kind of less vibration for open circle and solid circles are the same. They actually move together. There's no phase difference between these 2 oscillations for open and closed circles. And this is the lower energy excitations compared to the other optical phonon modes, where the open circle and the solid circle are going against to each other. For example, they actually are doing this kind of motion, that when the open circle move downwards and the closed circle actually move upwards, so they actually go against each other. So either they get closer to each other, or they move away from each other, for example. So in other words, they actually go like this, so they can actually get further apart, or they get closer. Okay, so they have the relative phase out of phase with respect to each other, and at the same time, this kind of a vertical vibration is actually perpendicular to the propagation directions q, which is the horizontal direction. And so this is exactly what we call this transverse mode. And for acoustic, so the lattice vibration is along the same direction of the wave propagation, or the momentum direction. So to illustrate this in a cartoon picture, so let's just use the same cartoon picture that I just used before, that in the realistic solids, all this lattice vibration oftentimes carry charge, because you can imagine that the ion, when the ion move, there's some more or less electrons can actually come closer to the ion position, so that the charge of the ion is actually doing this kind of lattice vibration along with the ion vibration. But for acoustic phonon modes, this kind of a charge, vibration for the ion charge doing this kind of a horizontal motion or lattice vibration, which is very much like the sound propagation. For the sound wave propagation, we know that the atoms of the molecules in the air actually are doing precisely this kind of a pressure-induced vibration, where the sound propagation is actually along the same direction of this molecule vibration. Okay, so, and acoustic by definition is something related to the sound. Okay, and therefore this kind of a acoustic phonon mode, shows exactly the same kind of a vibration as the sound propagation. Okay, namely the atoms vibrates along the same direction as the wave propagation. And so it is a longitudinal phonon mode, and the X energy is actually very, very small. It can be almost zero as Q goes zero. Okay? And this is a very low energy excitation, because you can imagine that it costs almost nothing to simply just vibrate this ions a little bit along the same direction of the wave propagation. So it can be a low energy excitation. Whereas in the optical phonon mode, you get opposite charges along the different direction, different positions, and they can actually move either closer or to the far away from each other. Okay, so effectively, when they carry charge, there is electrical polarization associated with such a kind of out of phase vibration, and that is the reason why we call this optical phonon, because optics means that we have electromagnetic wave, right? So since we generate indeed electrical polarization, so there is an electric field, and therefore it is related to the electromagnetic wave, and namely the optical phonon. Okay, so the atoms vibrate against each other, and they can generate electric polarizations along the direction which is perpendicular to the wave propagation. And so it is called the transverse phonon mode, and it costs energy. And the reason why it costs energy is because it generates electrical polarization, which increases the energy of the system. Okay, so finally, we will calculate this thermodynamics of this phonon. Okay, and we will take the Debye model where we could study the kind of a phonon-assisted tunneling event, and then we calculate that phonon contributions to the total energy of the system, and we further calculate the specific heat, CV, of the system by taking the temperature derivative of this E bar, where E bar is the average energy of the system. And by statistical mechanics, we know this, how to calculate the E bar. This is simply just an ensemble average of this Hamiltonian expression value of the Hamiltonian at the finite temperature by taking the ensemble average. But we know that this could be second quantized in terms of the phonon number, NQ plus 1/2 times h bar omega q, where omega q is the phonon frequency. And at the end of the day, this E bar is nothing but summation over this normal mode variables times the phonon energy and number of phonons plus 1/2. Where the average phonons is actually satisfying the both statistics, namely this satisfies Bose-Einstein distribution. Okay, so let's stop here for now, and next time we will start to calculate thermodynamics of the phonon, and we can compare our theoretical predictions and calculations based on so-called Debye model, where we could make some approximation to calculate density of states of these phonons. And then we could use this linear dispersion of the acoustic phonon mode at low energy and low momentum limit, and then we could estimate the temperature dependence of the specific heat contributed from the phonons. So see you next time.